going to do today is go over kind of the abstract business of last time fairly quickly. And again, the definition of what a Lie algebra is and what a Lie algebra representation is. And then stop for a minute. And if you have any questions about anything I was talking about last time, if you can hold them for a few minutes until I summarize that, and then we can, it'd be great if there's things that you're still finding confusing about that from last time, we could talk about those. And then what the next thing will be, today we're going to go down to something which is much more concrete and about a very specific group, really about the group of rotations in 3 dimensions, and talk about, you know, how this general theory about Lie algebras works in the case of the rotations in 3 dimensions. And then I'm going to spend a lot of time on explaining a different way of thinking about how to do rotations in 3 dimensions. It's based upon quaternions, which is something that you often don't see, but it's actually an easier way to compute things in 3 dimensions, and it turns out to be something, you know, which is kind of appears crucially in quantum mechanics. So let me get started with that. Okay, so last time, let's see, what did I do? I told you about, so last time we had G was a Lie group. Well, let me just say it this way, it was a matrix group. It's a Lie group given by explicitly, the elements explicitly given by matrices, and the group actually is matrix multiplication. And then Lie G was a it was really the set of the matrices X such that e to the, and if you exponentiate some parameter times X, you get something in the matrix group. And in particular, t is equal to 0. This always has the identity, which is x equal to 0. And in some sense, you should think of this as being, as t increases, it tells you what elements of the group near the identity look like. Okay, and then the so that's called the Lie algebra, and you can also think of this. So geometrically, this is the same. This is the same thing as the tangent space to G at the identity. That's the one abstract way of thinking about it. Okay, then the tricky aspect of this thing, the extra structure that comes in here, which is due to the fact that which reflects the fact that you're dealing with a group, that these things lie in the group, is this so-called Lie bracket. And the Lie bracket, let's see, is so you define just here the Lie bracket is just the commutator. It's the thing you get by multiplying the you get by multiplying the matrices one way and then the other way by subtracting. My PC wants me to optimize it, which I'd rather not do right now. Okay, so and then one fact which is proved in the notes is that if x and y are in Lie algebra, then when you do this to them, you're going to get another matrix which is also in the Lie algebra. And so this is also in the Lie algebra. This is also something that you can exponentiate and get something in the group. Now then there's another. So to understand the significance of this bracket, other than just this kind of fact about multiplication of matrices, there's something that that's shown in the notes is that this is also the thing you get, that if you take y and then conjugate him by e to the tx, so e to the tx, and then the inverse is e to the minus tx. Okay, so this gives you an action of the group on the Lie algebra, and this is actually what's called the adjoint representation Lie algebra. But the one significance of this is that this is what you get if you do this, but just and you just look at it infinitesimally. So in other words, just take the derivative with respect to t of this at t is equal to 0. Okay. If you do kind of this conjugation kind of, and look at its rate of change at t is equal to 0, that's another way of understanding what this guy is. So that this guy, you sometimes should think of him, if you see him, is he's telling you what, if you take y and start conjugating him by the exponential of this guy, this is going to tell you what the rate of how this guy changes when you conjugate him by this guy infinitesimally. That's what this formula says. So we're going to see this formula very often later. That's why I wanted to emphasize it now. And then after class last time, I mean, somebody reminded me of there's another way of understanding the significance of this, and there's something called which I don't want to. I guess maybe we may see this in another context a little bit later, but there's something called the BCH formula. And that says that if you take e to the tx and you multiply it by e to the ty, well, that things behave. I mean, if x and y commuted, you could just use the properties of exponentials to get e to the t x plus y. Okay. So this, if x and y are commuting things, then the kind of standard properties of the exponential work, and you just get this. But if x and y don't commute, if this commutator is not 0, then what you get is you get you get in the next you get a t squared term here, which is has a half, and then xy. Okay. Yeah.
I'm sorry. Is the derivative formula, is that supposed to be e to the negative txy there, or is that just t to the negative x, or e to the negative tx?
Here.
Yeah. Is the second term in that derivative supposed to be negative txy, or is it just tx?
Just tx. Sorry.
Okay.
Okay. It's just tx. So it's just you got a group element e to the tx, and then the inverse group element is just with a minus sign.
Okay.
Okay. Yeah. And so then for something completely different, but you do this, and the reason I'm not doing this is because in general you get a very long and an infinitely long series here, which is hard to understand, which depends upon the commutators. But it's there's going to be a t squared term here plus etc. Anyway, and so another way of thinking about why the significance of this guy is that he's if you think about the group multiplication, that the group multiplication is just the normal commutative is a normal commutative law plus the first order and to the next order in t something which just depends on this commutator. So if you wanted another kind of motivation for why this guy is interesting, is that he's capturing the non-commutative nature of the group law, and that he's kind of infinite. He's kind of telling you what it infinitesimally looks like near the identity. And so these are just kind of two different. This we may use in a special context later. This is going to appear quite a bit. But anyway, so this is just a more practical stuff about the Lie algebra. But anyway, this is I guess all I want to say about Lie algebras. And then let me quickly say what the standard examples are. That's this. And so the examples that you should know about, that you should always have in mind, is that if you take all invertible real or complex matrices and look at the Lie algebra, then you're going to get all real or complex matrices. So this is all matrices. It includes zero. These are not necessarily invertible. This is but if you take any matrix and start exponentiating it, and exponentiate it, you're going to get an invertible matrix, and that's so that's this general Lie group of all invertible matrices, and its Lie algebra is the general, just the general matrix, either real or complex. But then you have kind of subgroups of this which satisfy certain conditions, and one was the orthogonal group. So this was the real n by n invertible transformations that preserve an inner product, and this is equal to a set of M such that the transpose of M is minus M. Okay, and so this is what I'll often say, that a matrix is antisymmetric when I say this. In other words, that if you flip it about the diagonal, you get a minus sign. And then for the algebra of UN, you get the same thing, except because you're preserving the Hermitian inner product, you also have to put a conjugation in here, and you're going to get the complex matrices such that the adjoint, which is the transpose conjugate, is minus M. And these things, if M were M adjoint, we would say it's self adjoint. These things I'll often say are skew adjoint or anti-self adjoint. And then one last thing, I don't know if I said this last time, is that if you've got the subgroup of these guys that has determinant 1, then that's SUN. Then you also, so it's this plus there's an extra condition. There's a condition that ensures that the determinant is 1, and the extra condition is that the trace of M is 0. Okay, and the way you show this is there's a formula that's not too hard to show in linear algebra, which is that you use the determinant. Well, so since the determinant of a matrix is the exponential of the trace of the matrix. Yeah.
Sorry, is it determinant of the exponential of n?
Now I'm confusing. I've confused myself. E to the, sorry. No, I mean the point is, okay. Now I've confused myself. I
think Leo's right. Actually, looking from the book, it's the determinant of e to the n equals e to the trace n.
Okay, I guess you're so sorry. So there seemed to be something wrong about this, but that makes anyway. Okay, that's I have to think about it for a minute. That's much more plausible, but I'm still confused. And anyway, the way to tell which is right, I think this is right. I think you're right. Is that just think about a diagonal matrix. If it's a diagonal matrix, the determinant is just the Anyway, yeah. So I think this is right. Okay. Or is it right? Anyways, sorry, I should have thought again about this, but there is a formula that relates the determinant to the exponential of the trace, and it just changes the fact that you're taking on one side the product of the diagonal elements, and the other side you're summing the diagonal elements, and then when you exponentiate, you turn a sum into a product, and I'm still confused. I'm still confused. But anyway, there is a formula like this relating the determinant of the trace will give you this, and then the determinant being 1. Anyway, I don't know why am I finding this confusing? Why is?
Yeah, you just look at the Jordan form of M, and
yeah, that's what I mean. Yes, so sorry. So M should be yeah, if n is lambda 1 to lambda n, then the determinant is the product, and e. Okay, yeah, I think that's right. That's right. Let me leave that. Okay. Yeah, I didn't really want to get into this, but the so this unitarity condition, this skew adjointness, and then this trace-free condition gives you the lead that you're in the determinant one condition. Okay, so but those are pretty much the main examples that I wanted to talk about, and maybe just a few more comments about so the algebras. Maybe I won't. Again, someone asked me after class, why the name algebra? Well, the name algebra is you've got some way of combining x and y and producing this bracket xy, but it's actually not a normal kind of algebra. It's because if you think of that, if you think of x, y, and the bracket of x, y as a product, it's not an associative algebra. So the name algebra is a little bit weird in terms of other terminology you may have seen from abstract algebra, but this is it is what it's defined to be. Okay, and then you can let me go. And the thing that I was really the thing that we're really kind of want to focus on, and that in some sense this course is all about, is about what happens if you work with representations in terms of the Lie algebra and not in terms of the group. And so there's a notion of a Lie algebra representation. And this is just a linear map phi that takes the Lie algebra. Let's see how hard to write this down. Takes up two just matrices, and again, we're going to work with complex representations. So this Lie algebra is a real vector space, but here we're working with complex representation. So we want this to be complex, and then so it's a linear map from there to there, and that preserves the. So you have an analog of this homomorphism property, which is that phi, if you take phi of x and phi of y, and okay, so these give you two matrices. If you take the commutator of these matrices, or the bracket this is in the Lie algebra of GLN, then you're going to get phi of x, y. And these are the gadgets that we're going to find most interesting in quantum mechanics, because it's these, these are kind of linear operators on finite dimensional vector spaces. But in general, we're going to be interested. So we're going to be interested in a situation where you've got some kind of group acting. You look at its Lie algebra. You've got a representation that gives you a bunch of operators, one for each element of the Lie algebra. And those operators are actually going to be the observables that you're showing up in quantum mechanics, things like your momentum operator, your angular momentum operator, etc. So that's where this is kind of why this is a central gadget. But right now it's just it's kind of a little piece of algebra right here. And then maybe just the last thing to say something about this is that okay, so one thing, if you've got a so if you're given a representation of G of G, so it's pi representation, pi on some vector space V, then if you take in some sense, if you think of this as a map between the Lie group and GLN, you take its derivative, phi equal the derivative at the identity of this thing, which I talked about kind of abstractly last time, is a Lie algebra representation. And then it turns out actually, so for the for the cases that we're interested in here right now, where the representation is on a finite dimensional vector space. So for V, finite dimensional. And if phi of the G representation implies that pi of e to the tx is equal to, okay, and I guess I probably also need to, I actually need to put a condition on the group, which I'm not saying right here, but anyway, let me just say this part of it, that this is phi is e to the t phi of x is a G representation. Okay, so this is called the kind of integrability problem. And if somebody hands you a representation that kind of just knows about the just a Lie algebra representation that just knows about the Lie algebra, by exponentiating, can you actually get a group representation? And it's going to anyway. And so for most examples we care about where V is finite dimensional, that this is going to work. You get into trouble, especially if V is an infinite dimensional space, then you may not be able to make sense of this exponential here. Okay, so that's I think that's the end of the general nonsense I want to say. Oh yeah, so sorry. One last thing, then is that the I need to say one more piece of generalities about Lie algebras. Is that so there's a representation called the adjoint representation of G. So this is something that we'll call, instead of writing pi, I'm going to write capital AD, and then the vector space is on the Lie algebra G, and this is given by that add of G applied to X is G X G inverse. Okay, so you can conjugate the algebra elements by group elements, and they'll stay in the Lie algebra, and that's going to and this gives you a representation that's called the adjoint representation. Now, if you use that formula that I was claiming is so interesting about e to the tx, y e to the minus tx, and if you differentiate it, that gives you the derivative of this guy, and so then the adjoint, you get the adjoint representation of the Lie algebra. And this will write with a small a, and so it's in some sense just this add prime. It's just the derivative of this guy, and so you write it with a small d, and add, and again it operates on the Lie algebra, and the way it operates is that add of x applied to y is just x, y. Okay, so there's this general package of this relationship between a representation of the group and a representation of the algebra, and for any Lie group, the fact that just the very existence of the algebra says that there's kind of a distinguished representation, the adjoint representation, and if you take the course, if you differentiate and get the corresponding Lie algebra representation, it's small ad. It's again, it's a different way of understanding why the commutator is interesting. Okay, and so maybe so this is enough of the kind of and then just the one kind of caveat to watch out for is that again that this is a real vector space, and you really want to complexify and turn it into a complex vector space in order to apply our general theory. But we'll talk more about that when it becomes important. So this is kind of the abstract nonsense from last time. Are there any kind of questions about any of this? Is there anything that you were confused about last time that this hasn't clarified? Or
Professor, a question of analogy, more or less. In the derivatives I'm used to, you tend to take the derivative at a location in the original, in your original domain, and then that gives you a different derivative from where you would get it elsewhere. So is there any sense of taking the derivative of the adjoint at a certain point in the Lie algebra, or is this a different sense of derivative?
Derivative. Okay, so I mean, this derivative. When I'm using this derivative here, I'm always meaning that you've got a map from. So you've got add it's one of these pies. So it's a map that takes G to GLN, and there's this problem that it's really R, but anyway, maybe it's R. But so it's just this very abstract notion of taking. You've got a map between two smooth manifolds, and you're taking its derivative, and you're taking it always at the identity. Now, the thing that's different about the thing that's kind of very special about Lie groups is that they're very, very homogeneous. You can get from the identity to any other point in the Lie group just by multiplying by that group element. So once you understand what's happening at the identity, then there's kind of simple formulas which kind of tell you how to transform that calculation to any point in the Lie group. It's a little bit hard to keep track of because you have to keep track of the difference between multiplying the right and left. So it's a little bit of an annoying technology to do. But knowing whenever I put derivative here, I really mean derivative at the identity. But I'm implicitly using the fact that if you actually know that, then you can just do a G multiplication and move the identity wherever you want. Does that help?
That's really helpful. Thank you.
Okay. Any other questions about this abstract nonsense of Lie algebras, Lie groups? So, because
I have a question.
Yeah.
So this adjoint representation of Lie G, that's a representation of Lie G on itself, right? The vector space that representation is acting. Yeah. And so, like this representation, normally you have the representation of some matrix group, or just some group, and you have a map pi which brings elements of that group to some matrix group, GLN of C, and then that acts on some vector space. Right. But in this case, all those three pieces are the same. They're all Lie of G, right?
Let's see. Yeah. Okay. So for maybe let me just say this again. So an arbitrary representation, what you've got is it's really a homomorphism that takes an arbitrary group to invertible matrices. So it's taking G goes to pi of G, right? Okay. Now so this is a Lie group representation. What I'm saying, so a Lie algebra representation is something that takes. So you're feeding this guy group elements. Now this is somebody that you can feed him Lie algebra elements. So Lie G, and it's going to take X. So it's going to go to and then now it's not to invertible matrices. It's not to this group. You're not taking one group to another. It's not a group homomorphism. It's just a linear map from this vector space to this other vector space. And the vector space is the Lie algebra of this. It's this guy. Okay? And so a Lie algebra representation is taking any element of the Lie algebra and putting it and giving you an operator on n-dimensional complex vector spaces, a matrix which is the phi x. Okay, and so here, n is the dimension of the representation, and same thing here. Okay, I don't know if this helps. So but if you've got if your group is a matrix group, then it's true. So this is going to be this is going to be again. These guys are going to be matrices, but they be matrices satisfying some particular condition, definitely. Same thing down here, that these, if G is a matrix group, then it's Lie algebra. Again, it's a Lie algebra of matrices, but these matrices that are in here satisfy some particular condition, like being, antisymmetric or skew adjoint or something like that. But it's so what a Lie algebra representation is? It's basically a linear map that you feed it anything in the Lie algebra, and you get a linear operator on some dimension n vector space. Okay, and what's I think confusing at this point is all of the examples that you've seen of this. This is just the identity. Yeah, so if you use the defining representation where this is just kind of just the identity, this is just the matrix sitting inside here. Then if you take its derivative of the identity, then this is also just going to be the identity. So the examples you've seen are a little bit too trivial, but you get, as time goes on, we're going to see more and more examples where you can start with fairly simple Lie groups, so kind of small dimension, and you can produce interesting representations of large or even infinite dimension. So this side is going to be, but the idea is that this side is something pretty simple. This side can get arbitrarily complicated as you look at more and more complicated representations, and these can be very, very large matrices or infinite dimensional, or linear operators on an infinite dimensional space. Does that help?
Yeah, thanks.
Okay, any other questions about this stuff? Okay, so if not, let me then get on to the newer stuff I want to do today. So what I'm going to do today is kind of two things, and this is all stuff. There's a lot going on in this chapter 6 of its notes, and the first part of it is really just to try to explain, to tell you how this story works in a special example, which is the case of rotations in 3 dimensions. So let's just start by doing that. So we're gonna look at it. We're gonna look at one specific Lie group, which is SO3. Okay. So, but maybe before I talk about rotations in 3 dimensions, let me first do SO2. So rotations in the plane. Well, any rotations in the plane are gonna, these group elements are going to be given by, a rotation counterclockwise by an angle theta is just going to be given by these matrices. Okay. Right. And I could have argued that that this was actually maybe not that you're actually better off if you wanted to talk about such rotations, you're better off picking identifying the plane with the complex numbers and using e to the I theta. It's a lot easier to manipulate. Well, we're going to do something similar in 3 dimensions. I'm going to tell you about what happens in 3 dimensions, and then I'm going to argue that there's actually a better way to do things, that you should do the analog of complex numbers for 3 or 4 dimensions. We'll get to that in a minute. But this is all there is. And then if you want to take the if you want to ask, what is the matrix that if you exponentiate it, it gives you this. So this is equal to e to the theta times a matrix L, where L is equal to 0, minus 1, 1, 0. So just expand, start taking powers of this, and again you'll see that the odd powers just look like this, the even powers are just the identity, and you get and if you put in a theta, you get the formulas for the cosine and the sine here. So the Lie algebra of SO2, is one real dimensional. It's really, as a vector space, it's just the real numbers. But when you get, but it's the, you can think of it as being all 2 by 2 matrices with proportional to this. So it's so as a basis is L. So you could also think of it as the kind of anti-symmetric metric 2 by 2 matrices. It's all things of this form where you just multiply, put some kind of constant in there. Okay, so that's real. So this is how it works. Now the thing about 2 dimensions is it's a commutative group, and so that there is no if you take the bracket of this, the commutator of this with itself, you're going to get 0. So there's no non-trivial commutator, and there's no non-commutativity in this group. So to make it more interesting, you have to go to 3 dimensions. 3 dimensions is where you first see a non-triviality bracket and things aren't commutative. So SO3. Okay. So I defined kind of SO3 matrices as all matrices that preserve the standard inner product on R3, and you can think of, and it also preserve the orientation. So you can think of these as matrices that satisfy this condition, that their transpose is their inverse and that they're of determinant plus 1. But if you want to kind of actually get your hands on these things and start parametrizing these things, you kind of immediately have a problem that they're a lot harder to manipulate and a lot more confusing than these guys, which are just kind of a 1 parameter simple family of these things. And so one thing you can do is you can write, so an arbitrary, you write an arbitrary element as a product of rotations about the axes, the possible axes, about the coordinate axes. So for instance, if you want to rotate, if you want to do a rotation in 3 dimensions, and one kind of rotation are just rotations about the x-axis, and these things are going to look just like this. So rotating by theta about the about the x-axis or about the unit vector in the x direction is going to be given by, you just take 1. Just write this in. So 1, 0, 0, 0, 0. So in terms of the 1 coordinate, you don't do anything. But in terms of the 2 and 3 coordinates, you rotate in the 2 and 3 plane using this guy. So it's cosine theta minus sine theta, cosine theta. Okay. Anyway, and then I won't write out the other formulas, but you can then write out the formulas for how to do a rotate about the the other axes just by by interchanging, anyway, by permuting the axes on this matrix. And you just have to watch out that if you anyway, the formulas are the notes. I don't want to write these out, but you can find you can see what happens if you try to rotate about the 2 axis, and what happens if you try and rotate about the 3 axis. Okay, and they're just, I mean, just the one moves here or here, and the other guys move around to give you the appropriate thing. And you just have to watch out. Yeah. if you want to get the signs right, the minus sign here, you know, the sign flips here because anyway, but because of the way this, you want this to be SO3. You want this to give you a to give you, well, and you want to get a rotation in the correct direction and so you have to worry about a sign as you go along. Okay, but now, so so then if you want to know about, so one thing to say about rotations in 3 dimensions is that you can kind of, you can generate any one you want by, you know, as some product of these guys, some general rotation about these things. If you know that your general rotation corresponds to first rotating about one axis by this, and then the other axis by this, and the other axis by that, then you just multiply out your matrices. And what you find if you do that is that you quickly get some really kind of complicated looking 3x3 matrix with all sorts of complicated trig functions, complicated combinations, the cosines and sines in it, and trig identities that turn it into other things, and it quickly becomes a mess. And there's a long story about how to do this. There's also different ways of parameterizing rotations. One is by Euler angles, which you may have seen. I won't tell you, but the idea is that always that you generate a 3x3 SO3 matrix by some product of some simpler rotations. Okay. Now, if you want to, we're interested in Lie algebra. So the Lie algebra of these guys. So again, these guys, you can see are exponentials of something like this, but they're going to be, I'm going to write, so the Lie SO3 has a basis given by, so this space is a complicated nonlinear space. This space is going to be a vector space. It's going to be a 3-dimensional vector space, and its basis is going to be given by infinitesimal rotations about the 3 axes, which are going to correspond to, so I'll call it L1 is, it's going to be 0, 0, 0, 0, 0, and then 0, -1, 1, 0. And L2 is going to be, you're going to have, it's going to be 0, 0, 1, 0, 1, and then more 0. Sorry, this is the minus sign, 0, 0, 0, 0. And L3 is going to be just this guy, but with this guy moved down here, so it's 0, -1, 1. Okay. So if you really, so the Lie group is hard to parameterize, and it's very hard to get your hands on. The Lie algebra is actually quite easy to parameterize. It has a nice basis, or if you want, you can think of this as just, you know that the algebra elements of SO3 are antisymmetric matrices. So you can ask, you know, what's the nice basis for the antisymmetric matrices? Well, it's clear that any antisymmetric matrix has to have zeros down here, and it's going to have the 3 numbers are going to be determined by knowing what happens on the above the diagonal, and then just putting a minus sign on the other side. So this is the Lie algebra of SO3 is just R3 is just a 3-dimensional space, and it's the antisymmetric matrices over the real numbers with this space, and this is a nice basis for it. Okay. So you can see the Lie algebra is something much simpler than the Lie group. But now let me so you can ask, what about the brackets? So it's easy to compute commutators of any of these things. So let's just do that. Maybe. So the Lie bracket if you take the commutator of anything with itself, you're going to get 0. So the non-zero ones are going to be that if you compute the Lie bracket of this and this, you'll get that if you do the computation. 3. And then I won't write the other. And then one way to see what the other ones are going to be is just take this guy and then just do look at the cyclic permutations of this. So you kind of cycle through, move the 3 over here, and the 1 over here, and the 2 over here, and that'll give you another one of these relations, and you get all 3 this way. So I'll write this kind of plus cyclic permutations. And now at this point, you should know one thing you may notice is something funny is that this is the same relations we found for when we looked at the commutation relations of these xj's, which was, I think, minus I times the sigma matrices divided by 2. Okay. And it's also the same relations as for the cross product. That E1 cross E2 is equal to E3. So there's three things here. With the same, that you've got some 3-dimensional vector space of gadgets, and you've got this kind of anti-symmetric product on them, and it does the same thing on the basis. So it does the same. It's really an isomorphic structure. So we'll say this. I'm going to say more about this later, but just right now, notice that these are the same. So this is the Lie algebra of SO3. And this is the Lie algebra of SU2. And one thing that we're going to talk about quite a bit later is the fact that these are isomorphic, even though they appear to be quite different things. And that also not only are these isomorphic, but they're also isomorphic to this guy. Okay. Okay, so that's. Let's see if there's anything else I want to add.
I have a quick question.
Yeah.
So like if we just start with like the algebra of either SO3 or SO2, which turn out to be the same, and then we exponentiate them.
Yeah.
Then like the group element we'll get, I guess, will be the bigger group of the two. Like so, like what would be the lead group we get after?
Well, it's going to turn on. So this is what we're going to get to. I'm going to move on to in a minute, which is that it turns out that exponentiating 3 by 3, these you're actually going to get different things. You're going to get different lead groups. So you're going to get 2. Anyway, I think I should move on because we're going to see this in a different way. But this is what's really unexpected is that at the level of the Lie algebra, you have 2 groups that are the same, but globally they're not the same. And so this is what we're going to try to get to in a minute. Okay, and I think I better not let me move on to that. Get started on that because that's a confusing issue. There's some more things in the notes about explicitly thinking about explicitly asking yourself what is the adjoint representation. So one thing you might want to look at is to look at going through this exercise of what is the adjoint representation in these cases, not just what is the Lie algebra, what is the adjoint representation, and to explicitly write down what is small ad of x applied to y. How do you explicitly compute it if you have a basis and you have a commutation relation? Okay, but now let's move on to something completely different, what appears to be completely different, which is, and I think maybe a way to motivate it is that I said in the case of SO2, there's a good argument that you shouldn't really in your life, you really shouldn't be dealing with SO2. You should always deal with U1 because it's just a lot easier to play with e to the I theta than it is to play with cosines and sines. Well, there's a similar argument that all of this stuff you should never actually you shouldn't actually ever do it, because you should actually find an analog of e to the I theta, an analog of the complex numbers, which will make the calculations much easier. And so this is what I'm going to try to tell you about. So I hope people have seen this before, but there's this kind of higher dimensional analog of the complex numbers called the quaternions. Okay, and I'll kind of say what these are, and hopefully you've actually seen this before. If not, it takes a little while to get used to. But basically, and just as we use a C with maybe a blackboard bold to say we're talking about the complex numbers, these will often, if I use that symbol, I mean these guys. So this is as a real vector space. So it's isomorphic just as a real vector space. But just as the complex numbers are isomorphic to R2 as a real vector space, well, here these guys are, and I'm given by R4. But just as in the complex numbers, the new thing is that you can multiply vectors. You can multiply two complex numbers and get another complex number. Well, it turns out with the big discovery of Hamilton was that you could multiply elements of R4 and get another element of R4 and have a consistent way of multiplying and dividing and doing things. And that's these guys. So to make this work, you have to write your element of R4, right? Let's write. And I'll write the component, right? Well, let me just write it straight. So when I write Q, it's often that I mean a quaternion, just as kind of small z often means a complex number. Well, small q often means a quaternion. And so what it's going to be is going to be some real number, I'll call Q0, plus another real number times something I'll call I, because it's going to behave just like the complex square root of -1. And then some other one, but there's going to be some other ones called J and K. And so here all the Q's, Q, J's are real numbers. So these are four real numbers, and these symbols are kind of new symbols. They're playing the role of the square root of -1, but they satisfy some more interesting relations. Or so if you square any of these things, you're going to get -1. Okay. So they're going to behave just like square roots of -1, except there are three different square roots of -1. And this is going to, I mean, in some sense, this is where the analogy. I mean, the reason you could do two-dimensional geometry and when you had a square root of -1 is that you could, a square root of -1 told you how to take half the angle pi, where pi over 2 was. Well, if you're in 2 dimensions, there's only 2 ways of doing that. And in 3 dimensions, if you want to take -1 and find something whose square is -1, well, there's a lot of different, there's a whole sphere worth of ways of doing it. And these guys are going to tell you how to do that. But you can just think of them as algebraic objects that behave like this. But then you have to add some other. You have to add the fact that these anti-commute. So ij is -ji, etc. So these are not commuting objects. So all of a sudden we've entered a world of objects that when you multiply them, they don't commute.
Although A equals K, like I equals K. ij.
Yeah, I haven't. Yeah, and then also, oh, sorry. Yeah, that's true. But it's also true that ij is k. Yeah. So if you multiply this guy times this guy, you get this guy. But it's also true that if you if you multiply, is this right? Yeah. Yeah. If you multiply, if you take any two of these, and if you multiply them, you're going to get if you have to be very careful about the order. If you do it in the other order, there's going to be a minus sign. So these are the rules that, you know, once you know these rules, you can do this. Okay. Anyway, and then there's an analog of the conjugation, in that if you take q bar is going to be q0, and then you just replace, just as you replaced I by minus I when you conjugated, you do the same thing here with all three of them. So it's minus q1I minus q2j minus q3j. So there's a conjugation operation on the quaternions, which these things of this form are often called imaginary quaternions. There are things which, you know, change sign under conjugation, whereas this thing doesn't change sign under conjugation. Then to do computations, what you find is that then you find that the length. Okay, and so now that the connection to notions of length and to rotations in 3 and 4 dimensions is going to be that the length squared of this guy, if you think of him as an element of R4, his length squared is going to be q0 squared plus q1 squared plus q2 squared plus q3 squared, and that's going to be q bar. Okay. So it behaves just like the conjugate behaves nicely, like in the complex conjugate. You can get if you multiply something by its conjugate, you get its length squared. You get a real number and its length squared. Okay, so there's a lot to say, to play around with quaternions, but I won't do any more about this. Let me now tell you, what the relationship is between quaternions and rotations. And I want to argue that quaternions really are really the right thing to use if you want to think about how to rotate things in 3 and in 4 dimensions. And so let me. I think maybe I won't say the. Or let me just do this in 3 dimensions. Okay, so the relation, so using quaternions to do rotations. This is the, so here's the trick. So the trick is, what you do is you identify R3 with the imaginary quaternions. So the ones that have real part 0 quaternions. By just taking, I guess let me try to do it the way I had it. That if you take V vector by taking, so some vector V1, V2 with components, some vector with these components in R3, and you take this to an imaginary quaternion, which is V1 I plus V2 J plus V3 K. And I'm going to write this to follow the notation I'm using in my notes. I'll write this just with a standard kind of V vector thing. So now when you see a little vector symbol here, it means that I'm thinking of these guys as an imaginary quaternion. Okay. And now, then here's the trick. So now, okay. So consider what are quaternions. Consider quaternions U such that that u squared is equal to 1. Okay, so these are four-dimensional gadgets. You know, these are four-dimensional gadgets, but just look at the ones that have length 1, and these form a group. And you have to play a little bit to see how the formula for the inverse looks. But if you that's fairly simple. And then you could see that if you know a quaternion, you can figure out what its inverse looks like, and you can figure out that these guys form a group. These form a group. It's called and we'll call it. The name for it is just SP1. And you should think of this guy as really, I told you that I was looking for an analog of U1. I was trying to introduce an analog of the complex numbers and get an analog of EVI theta. Well, it's the analog of the group U1 is going to be these. So these are, instead of having unit length complex numbers, think about unit length quaternions. And so the space of these, instead of being a circle, it's going to be a three-dimensional sphere of unit radius. But we just call these SP1. Okay, then what you have is you have a map. Okay, so then you notice this. This you have to check is that the transformation V vector goes to U V vector U inverse is a linear transformation. You know, anyway, let me just is a linear transformation preserving in length. So in SO3. Anyway, you have to just check. This is fairly easy to check. Is that, you know, if you think of your vectors in here, identify them with purely imaginary quaternions, and then start and then, you know, use unit length quaternions to conjugate them. What you find is that this action on here, this is just, anyway, this is an element of SO3. It's a length preserving and thus length and angle preserving linear transformation, and it also preserves the orientation. And so, and the kind of so this gives you a fact, basic kind of mysterious fact is that if you take the map phi from which takes a unit quaternion U in SP1 and change and instead and changes it to this linear transformation which lies in SO3 goes to so this is things that the maps that take V vector goes to U V U inverse. this is an element of SO3. All right, this is a what you could check is this is a homomorphism. So what this means is if I do this, anyway, yeah. If I do this for U1 and I do it for U2, I get the same rotation in it as I would get if I did it for U1 times U2. Okay, so I don't. So this is kind of a tricky thing to get your hands on, to get your mind around, and there's a lot more about it in the notes, which I recommend. So we're going to spend some time talking about this. But what this says is that, you know, if you want to understand rotations, you should think of them not as taking an element of R3 and acting on it by a 3x3 matrix, but you should turn your element of R3 into an imaginary quaternion, and then just find the find a U that when you do this conjugation, it will give you the right rotation. Okay, so it's really it's a completely different way of thinking about rotations, and it involves just kind of unit quaternions, no more 3x3 matrices. Just like rotations in the two plane can be understood just using EVI theta. Okay, so now let's get into some of the subtleties of this. Okay. Here's a subtlety. Or maybe the main subtlety is that this is a this map is what we call a double cover. It says there are two, and let me say it this way: that two U give the same rotation. Two U, and it's actually going to be U and minus U give the same rotation. Okay, so what's if you think of producing rotations by conjugating by a U, the problem is that either if you put minus U here, the minus signs would cancel, and so it would give you the same rotation. And it turns out that it turns out, if you think about it, there are exactly two unit quaternions that correspond to the same rotation. So this map from this group SP1 to this group SO3 is a 2-to-1 map. Okay, and so then so it's what we call a double cover. And maybe to say a little bit about the trickiness of this double cover is that you often think about it is that you've got, if you're in SO3 and you do some kind of rotation. So you start out at the identity, and then you start rotating it. Let's say you rotate in some direction, you rotate about some axis. So then you're going to get a loop of rotations around here. So this is going to be rotations. So let's just take some loop of rotations. You start out with the identity transformation, and then you kind of just start doing something, and then you come back to where you started. Now, if you do the same thing, if you now for each, you know, so for the identity thing here will correspond to, if you start asking, well, what are the elements of SP1 that are kind of the inverse images up here of these guys? Well, one is going to have two things. It's going to have there's going to be one, but then there's also going to be minus one. Okay, so I'm going to think of this map phi as going down here. So 1 and minus 1 get mapped down to 1. Okay. And then for each point in this loop here, I'm going to get two elements up here. And what and the simple thing would be if you just had you know two circles here, but that's not what happens. What happens is something much more interesting, that as you go around, I mean, one way, as you go around, you get some kind of figure that does something like this. Let me make, I always get this wrong. Okay, and then it's going to come back down here. Now, if I've probably drawn this badly, but if you there's a better attempt at drawing in the book, but basically what you should see is you should see each point here is going to correspond to two points here. Okay. So sorry for the messed up drawing here. There is a better picture in the book, but you're gonna what this is now what have I've really messed this up. Okay. Let me make a little bit better attempt here. So what do I need to do? I need to start at 1, and then I gotta I don't know. Anyway, I'm sorry, but you can see my drawing skills are really not what they should be. But you see, you start at 1 and you go around, and then you come back through -1, and then you go back around here and here, and then you come back to 1. Okay. And each point here corresponds to 2 points. 2 points here. Anyway. Okay. So anyway, so yeah, so this is it's a very hard thing to visualize, as you can see, and this guy is you can think of as being this guy. You should really think of these things as lying inside the sphere, the three-dimensional sphere in R4. These are unit quaternions, and then the fact that you're taking that you get a 2-to-1 map from here down to here tells you, it turns out that this thing is kind of three-dimensional sphere where you identify opposite points in the sphere, and that's called RP3. And so this is just the identify opposite points. So yeah, here you identify opposite points. Okay, so this is the, anyway, this is this mysterious picture. And now I want to, let me just say a few words, let me just say a couple words about how to do computations here. And then I'll come back, I'll start up with this again next time. But the, yeah, so let's just say a couple words about computations. Okay, so one thing you can do is you can do all your computations just in terms of quaternions, just like using e to the I theta, except now you've got ijk to keep track of, and then you just have, you're going to do a rotation about the w vector axis by using, using the n log of e to the I theta, and the n log of e to the I theta is e to the theta times that imaginary thing. So instead of just having I times theta, we've got some linear combination of ijk. Okay, and then so then what you're going to find is the so x vector, if you want to rotate x vector by, yeah, so to rotate x vector by angle theta about the w vector axis, what you do is if you're trying to do this in terms of 3x3 matrices, you'll find that it's kind of it's a truly horrible problem to try to figure out the formula for this. But here it's an easy formula. It's just if you think of these guys as being purely imaginary quaternions, then the rotation is just x vector goes to e to the theta, w vector, x vector, e to the minus theta, w vector. It's just the conjugation by this guy. Okay, but there's something a little bit tricky about this. Actually, this is the part of the trick and corresponds to this double cover, is that this isn't quite right. You actually have to put a 2 here, and you have to divide by 2. Okay, so if you want to rotate about by an angle theta, you have to use actually e to the theta over 2 times it. And this 2, so you can do this computation. This is a computation. I do it in the notes, but you can just do it using the properties of quaternions, and you'll see, and you can see that this gives you the right rotation about this axis, and this 2 also has to do with this kind of double covering. And as you go around, as you go around the circle once. As you go around the circle once here and do one rotation all the way around the w-axis, here up here you're going to go from theta is equal to 0 to theta is equal to pi. So you're only going to go halfway around. And if you go all the way around up at SP1, you're going to go around twice down in SO3. Okay, so I think I better stop that there now and then just tell you one last fact, which is where we'll start up next time. And so next time, okay. So what we one reason that people don't, that you probably don't see this whole story in a quantum mechanics textbook or very often, or even in mathematicians don't often tell you the story, because there is a way to avoid using quaternions. So next time, so what you can do is find that SP1 is isomorphic as a group to SU2. Okay, and so you can anyway. So let me talk about. Let me start with this next time. So so you can do everything. You can avoid quaternions, and you use 2x2 complex matrices. So it's possible to kind of use a lot of the same technology and to do a lot of the same calculations, and avoid having to introduce these weird new objects you haven't heard about, the quaternions, and then just stick to using 2x2 matrices. And you can see 2x2 just like these guys are non-commutative objects, 2x2 matrices are non-commutative objects, and there's a whole. You can now. I'll go through this next time, but you can see a whole set of you can see how the isomorphisms are going to work. It's going to take things like ijk over here are going to turn into the Pauli matrices over here, and you see a lot of that. Okay, so let me. So next time I'll tell you a bit more about this story, how to get how to go from quaternions to 2x2 matrices, and then you'll also then you'll realize that you have the same phenomenon that SU2, SU2 is a double cover of SO3. So SU2 is also a three-dimensional sphere. It's a double cover of SO3, and this is also sometimes called spin 3. Okay, because so it will turn out that this story that I'm telling you here is very special and only works in 3 dimensions. But there's a general phenomenon that if you do rotations in any dimension, there is a group which is a non-trivial double cover of the special orthogonal group called the spin group, and it has a lot of the same properties. To understand spin groups and arbitrary dimensions is really a long story and quite complicated. But in 3 dimensions, spin 3 is really just the unit quaternions. It's easy to understand. Okay, so better stop here. So any quick questions now before I stop, and then?
Yeah, quick question.
Sure.
This might be what you're getting into next time, but what are the differences of why would you not use the quaternions versus the 2x2 matrices, or vice versa? Is there advantage to disadvantage, or is it just a matter of preference and not learning new convention?
I think it's. I mean, they're completely isomorphic mathematical objects. You can do your calculations either way. I mean, I think. I would say that the reason for the problem, in some sense, the beauty of the quaternions is that I'll say at some point also what happens in 4 dimensions. In 4 dimensions, you can also use quaternions. They also work very, very nicely. So if you were just interested in how do I do rotations in 3 and 4 dimensions, quaternions are really just a beautiful story, and they really are the way you should go. They always make your calculations as easy as possible. The problem is that it doesn't generalize, and so mathematicians and also most people feel that they'd rather actually learn a technique which generalizes and which they can use in any dimension. So so quaternions are basically perfectly designed for doing 3 and 4 dimensional rotations. They're kind of useless in other dimensions. Whereas if you think about SO3, everything I told you about SO3 matrices is also pretty much true for SON in any dimension. Okay, there's less of an argument about why you want to use SU2 matrices. It's just that's a bit more. I would say that some of that is actually just that people are. They never learned about the quaternions. They never learned about this in their linear algebra class, but they did learn about 2x2 matrices in the linear algebra class, so they're happy doing that. And there was actually kind of among mathematicians, especially in England, there was in the late 19th century there was kind of almost religious warfare between people who argued that you really should work with quaternions and to do geometry and try to generalize them somehow, and people who said, no, you should just work with matrices. And I think in some sense the matrix people won that war, but there certainly was a period in England in the late 19th century where you could find many people telling you that you were an idiot if you used matrices and not quaternions. Any other questions? Okay, so that's it for today. And again, I'll turn this off and turn back on the other Zoom session if anybody wants to stop by. Okay, bye now.